the diamond clue. What an extraordinary crystal reveals about the architecture of matter. Flint West reporting. Diamond gives us a clue, and it is hiding in plain sight. Ask somebody what conducts heat best, and instinctively, they are going to think metal, copper, aluminum, silver. Makes sense. Except diamond beats them. An electrically insulating crystal made entirely from carbon can conduct heat several times more effectively than copper. Now, that is interesting, but the important part isn't that diamond conducts heat extraordinarily well. The important part is why. Because carbon can become graphite, carbon can become graphene, carbon can become diamond, same basic ingredient, completely different behavior. What changed? The architecture, the bonding changed, the geometry changed, the dimensionality changed, the lattice changed, and suddenly the physical properties changed with it. That gives us the first principle. The properties of matter arise not merely from the ingredients, but from their architecture. And materials science already knows this. We manipulate crystal structures, we introduce dopants, we engineer defects, we stack materials only atoms thick. We can even rotate one atomic lattice against another. Twisted bilayer graphene proves the point beautifully. Change the geometric relationship between two sheets of carbon, and electronic behavior appears that neither sheet possesses independently. So now the question changes. Instead of asking what material has the property we need, we start asking what atomic architecture would produce the property we need. And now we're getting somewhere. This content is brought to you by Bobby Giggs. Promote your brand here and reach a wide audience across platforms like YouTube, Instagram, and Facebook. Follow the links in the description to get started. Take room temperature superconductivity. Maybe the problem isn't simply finding the right element. Maybe it is finding the right combination of electronic structure, lattice geometry, bonding, carrier density, interactions, and stability. Computational materials science is already searching enormous numbers of hypothetical structures looking for precisely these kinds of combinations. But then we hit the wall. Because predicting a structure is one thing, making the damn thing is another. Atoms don't read blueprints. They respond to thermodynamics. They respond to kinetics. You can design the perfect structure on a computer only to discover that it is unstable, impossible to manufacture, requires enormous pressure, or simply turns into something else when you bring it back into the real world. And that means there are really three problems: property, architecture, pathway. First, what do we want matter to do? Second, what atomic structure makes it possible? Third, what combination of temperature, pressure, chemistry, deposition, strain, and environmental conditions persuades those atoms to assemble into that structure and stay there? That's where the CRISPR analogy breaks down. Biology has DNA. It has a molecular template and machinery capable of reading and reproducing those instructions. Inorganic matter doesn't. We are increasingly learning how to design the blueprint. What we don't yet have is a universal atomic construction system capable of building whatever architecture we specify. And that may be the real frontier. Because the future of material science isn't simply discovering new substances. It isn't even predicting new structures. It is closing the loop between property, architecture, and synthesis. Diamond gave us the clue. The destination is something much bigger: the deliberate engineering of matter itself. Specify, structure, synthesize. Flint West signing off.